So I want to start by considering the potential energy of a 2 kilogram object that is 10 meters above the floor. Can you guys tell me, or would you be able to tell me, how much potential energy this object would have relative to the floor? It's a yes or no question. Okay, so please do so. Calculate it and tell me. I don't believe a calculator is necessary here. Anybody like to venture a guess? 200 joules. So this object would have a gravitational potential energy of 200 joules relative to the floor. Now, if I drop the object and it begins to fall, at some point or another, it is likely to make it to a point that is 2 meters above the floor. Is it possible for you to calculate how much potential energy it has now? Okay, so please do so. What you got?
40 joules.
That's right, 40 joules. It should not be a huge surprise that the object now has less gravitational potential energy than it had before. In fact, we would say delta U is equal to negative 160 joules. Delta U, meaning the change in gravitational potential energy. Now, during that time, gravity did work on the object. In fact, by what we talked about last month, the work would be equal to minus the change in potential energy. Now, if you don't like that, because this is a definition, when we talked about last month, that work and potential energy, when dealing with the conservative forces, are opposites, inverses. That by necessity, the work done against a conservative force is negative. Thus, work equals minus the change in potential energy. We wrote it this way, like that, but you understand these are the same statement. Now, this shouldn't be a huge surprise, and this is for the benefit of people who are still new here. We know a theorem, the work-energy theorem, that any net work done causes a change in kinetic energy. Because we know that theorem, I believe that we can look at this situation and recognize what that theorem means. If you don't understand, consider making this 2 and this 1. If I do that, I think all of you would agree that when the object is dropped, it will have a kinetic energy here, but it will also have a potential energy here. So by conservation of mechanical energy, the total energy 2 meters above the ground would have to be equivalent to the potential energy 10 meters above the ground. Well, if I solve this for the kinetic energy, correct? Well, kind of low here, so I hope that you guys also recognize then that this would have to be minus delta U, since delta, by definition, is final minus initial. And since work, again, is defined as a change in kinetic energy, this will also represent the work done. Now, none of this is a surprise. All of this is a consequence of setting a reference level at the ground and determining the potential energy and the kinetic energy based on that. Okay so far? Now, I'm using this to bridge a gap to something more difficult. So I want to start our trip across that bridge, if that's okay. versus this example is that this example that we're looking at right here has an artificial zero created because of a boundary of the problem. The object is dropped towards the floor, making the floor a convenient point of reference, but not an absolute point of reference. If that floor is in the classroom, we understand that, well, that floor is not really zero. There is no zero. There's no way for the objects to overlap, to be a zero distance apart, because both objects have extension. So we are never at the center of where the Earth is. We're always at its surface. We've chosen these levels artificially, and it's worked out pretty well because the force of gravity is relatively constant everywhere near the surface of the Earth, pulling the same all the time everywhere near the surface of the Earth. If I have two objects in space, one very, very far away from the other, we know that the interaction between them will be small, will be zero when they are infinitely far apart. We'll say it's small right now. That the object has a certain amount of gravitational potential energy at point A, and we'll call this A. If we were to drop the object from here, is it clear to you that that small, tiny little force will eventually cause the object to change location to here? Where once it reaches here, it will clearly have a certain amount of kinetic energy, but will also have to have gravitational potential energy here as well. Is that okay? It must be true by conservation of mechanical energy, and since there is no other force acting on this system, that the gravitational potential energy at A would have to equal the gravitational potential energy at B minus the kinetic energy. Plus the kinetic energy. This has to be true by conservation of mechanical energy. It should also be true that the work done in bringing the object here should be the change in kinetic energy. These theorems have to work out in order for us to have a unified contingent plan for how Newton's laws work in every aspect. Now, in order for us to understand the problem with this example, that's not true here. We have the capacity to find an absolute, a place where we know there is no interaction between the two objects, a place where we know there is no gravitational potential energy, a true zero. And that zero is when this location of the object is infinitely far away. We know that because of our definition of the force of gravity between two objects implies that there will be no interaction between the two objects as r goes to infinity, providing us a true zero. Now, to understand this true zero, we have to find a way of expressing the change in potential energy and going from someplace far away to someplace close. Now, we did that problem before. We talked about it. We talked specifically about looking at how much work would be done, which by definition is an integral. Calculating work is an integral. It requires that we sum up the force through every incremental distance that we move the object. And in this discussion, and there's a number of ways for me to do this discussion. In third period, I talked about the vector relationship between the two objects. What I mean by that, for example, we want to start with our object being infinitely far away from the object at the center, which we will call object 1, which means that r is drawn from 1 to infinity. the way I talked about this in third period is a reminder that this dot product is about looking at the relationship between the direction of the force and the direction of R. R is drawn in this direction, but the force on the object is in that direction. That's clearly 180 degrees. That's one way for me to describe this. Or we could do it in terms of dr and just put in that the force is negative. Either way, what we get for the work here is an integral of negative m1 m2 g over r squared dr that we're going to evaluate as the object moves from infinity to a distance r away from the central object, the planet or whatever. Now, this math we've done before. I'm only doing it out of respect for those of you who still struggle with your calculus. The first thing I'll point out is that m1, m2, and g are all constants, which means they will not change as the two objects get closer together. Because of that, they come out front. Now, I can take the negative sign out now, or I can take it out later. It's your call. I've decided for this class, I'm going to take the negative out now. Put the integral symbol here, and put this as 1 over r squared dr, which perhaps for integrating purposes would look better as r to the negative 2. Now from here, I got to do the mathematics. And the mathematics aren't all that tough, but again, sometimes it's not as obvious as I'd like it to be. So everything out here stays the same, negative m1, m2, g. But I'm going to take r and increase it by 1. So that'll be r to the negative 1. I'm going to divide by the new exponent. Everybody follow that okay? It's just doing the math of it. Which is going to produce m1, m2, g over r evaluated from infinity to r. Right, all the negatives cancel out. Now, here's where I'm doing things substantially different from third period I think will help. I could, of course, put any limits here that I'd like. I could have moved it from any two places. Like if I have an object here and I move it to here, well, then this would be R1 and this would be R2. Right, I could choose any limits. I chose my starting point to be infinity because I knew that would have to be a location where there's no interaction between the objects. But I could repeat this whole process and moving the object from one spot to another, any place between infinity and the surface of the object. So I'm bringing this up to indicate to you that what are we going to do here but do m1, m2, g over r minus m1, m2, g over infinity. Right? And recognize that that is the difference in the energy from the two locations. And this is the work done in getting it there. By definition, the limit as this term goes to infinity is going to make that 0, leaving us with the result, the work done in moving an object from one location to another, starting at infinity, is m1, m2, g over r. This also means I have to define the potential energy as being minus the work, which is minus m1, m2, g over r. Now, this again is by design. I need the work to be positive because if I drop something from infinity and it falls towards the Earth, when it gets close to the Earth, I need to have a positive change in kinetic energy. There's no way this term can be negative. Masses aren't negative, G's not negative, and R can't be negative. So there's no way for that term to be negative. I am explicitly stating, though, that we're going to define the potential energy due to gravity to be negative because of the way in which we define potential energy. Now, this doesn't make a lot of sense the first time you hear it, but it's defined this way because we chose a reference point where we knew there would be no interaction. That's why this works, but it's all based on reference. Our reference is infinity. That represents our place where we know there is no interaction between the two objects. Now, let me pause here and say you might not understand any of why this has to be true. It might not make any sense to you right now, but I have a simple example to prove why it has to be true that will satisfy our original example. Imagine I have a large object here, and I place an object a distance 2r away from that object, and I release it. Eventually, the object will make it to here, a distance 1r away. So this is my initial location, and this is my final location. If I release this object from rest, which means it has no kinetic energy, then as it traverses this distance, would you all agree it will be moving when it makes it here? That it will be falling towards the Earth or towards the planet. So when it reaches the final location, it will clearly have a non-zero kinetic energy. Everybody follow along with that statement so far? By conservation of mechanical energy, the energy here has to equal the energy here. So I can see that here I have energy of just gravitational potential, which by definition has to be minus m1 m2 g over 2r. But when I make it to my final location, the energy will be the potential final plus kinetic. Correct? Now, folks, this is the crux. This is what you should pay attention to. Kinetic energy can never be negative. The result of this has to produce a positive kinetic energy. And the potential energy here has to be minus m1 m2 g over r. That has to be true. So what's being suggested here is that for conservation of energy, to give us the expected result, now, do you understand that what we're looking at right here is not delta U? It's minus delta U. U final minus U initial is delta U. But more importantly, let's take a look at the answer. I want to make sure all of you see this big and bold. Let's do it right here. U initial has to be minus m1 m2 g over 2r. Minus negative m1 m2 g over r. Good so far? Negative times a negative is going to give me the positive. And we're going to get common denominators. So I'm going to multiply top and bottom of this one by 2 and make that positive. Follow so far? Well, 2 r's in the denominator, I'm going to get 2 m1 m2g minus m1 m2g, which clearly gives me m1 m2g over 2r, and it is explicitly positive. Does everybody see that? We define infinity to be the reference point, which by consequence makes our gravitational potential energy negative. It's not done by accident. It's done so that it all works out, so that Newton's laws are still acting consistently. The only thing we had to do to ensure that everything worked out correctly was be careful about what direction we're taking for R and F when we deal with the force. But nothing that we've done here is, trying to hide or hand wave it. It has to work out this way because of consequence. And your belief that potential energy has to be positive is a misguided belief in what potential energy is. Potential energy isn't something that an object has. It's an interaction between two objects. For this starting object here, to make it to here, it's falling into a gravitational well to which it would require energy to get out of. I want you to imagine the reverse case of this scenario. I have an object on the Earth. Understandably, it's trapped here. Do you know that we've only sent 2 objects out of the Earth? Only 2. Meaning everything else has eventually fallen back someplace. We've only been able to give enough energy to 2 objects to finally actually leave the Earth. And not just the Earth, but the Earth, Sun, the whole bit. It's hard to get away from the Earth. To take an object that's on the Earth and move it to a point infinitely far away. These objects are falling into a well to get to 0 energy. To get so far away that you're not moving, but you're not being falling back either, takes a lot of energy. I would have to give this object an incredible amount of kinetic energy to do so. And it would just get it to a point where it's outside the influence of the Earth. A point infinitely far away. And at that point, the object would have 0 energy. Because it starts out with negative potential energy. By consequence, if it was able to leave the Earth and get to a point where it would stop, it should have no energy when it gets there. If we made the potential energy positive here, that would never work out. By the way, what we're talking about here is something called the escape velocity. The amount of energy required to escape a gravitational well comes from looking at the energy necessary to bring your energy to 0. The escape velocity is the amount of energy required, the amount of kinetic energy required to bring an object from a negative gravitational well to a point where it has 0 energy. Talked about the fact that if you have 2 objects, we know that the force is a vector. So we have to find a way to define the vector direction of the force relative to how far apart they are. So we talk about the force on 2 from 1 being relative to the distance between 1 to 2. Meaning we draw an arrow from object 1 to object 2. The direction of that arrow is r hat. The force must be in the opposite direction of r hat. So the force ends up being negative from these points of reference. We okay so far? Remember,